I'm way far behind. So we're going to really pick up the pace, and it's going to be exciting. So I want to start talking about RAII. Resource acquisition is initialization. Just rolls off the tongue, doesn't it? Every time Bjarne says that, he points out that he takes the credit for it, and then he thinks it's awful. So it's like, it's a really bad marketing idea. But that's what resource initialization is. Initialization. This is used all over the place. The standard uses a ton of these. I'm not going to go into a whole bunch about other examples. But the idea is I'm creating an object that has a resource, and it's going to try to acquire the resource in its constructor. And the question is, what happens to the object if acquisition fails? And the answer is, I skipped too far here. There we go. The answer is nothing. What do I mean by that? What I mean is that if acquisition fails, we're going to throw an exception. And if we throw an exception in the destructor, then when has the object begun to live? When is the beginning of an object's lifetime?
Constructor.
Is that what I said? I'm sorry. Okay. We're going to throw an exception in the constructor. Yes. And when does an object's lifetime begin? When we complete the constructor. And the constructor, therefore, will not be completed. Therefore, the object never lives. And that's why I say nothing happens to the object. If we don't acquire, the object doesn't exist because we've thrown an exception, right? So what we've actually done here is we have mapped an object's acquisition into the existence of an object. Resources acquisition into the existence of an object. If the object exists, we got the resource. If we didn't get the resource, the object doesn't exist. So what is an RAII? It says that the destructor has resource release responsibility. Sometimes objects will have a release member function, which basically says somebody else is going to clean it up. You don't have to worry about it. But in general, the idea is that this object is responsible for cleanup of a resource when its destructor is called. And remember, cleanup cannot throw, which means the destructor cannot throw. So we have this design guideline, which is that a function or a type, any item, should do just one thing. That's a nice design guideline. When you start having, and this is my own personal failing, I'll write a function which is small and simple, and then I realize, oh, I could do one other thing, and then pretty soon my function is this awful thing. Or classes are the same way. But the really nice design is a really clean design where if you see you have a class that's really doing two things, let's make it two separate classes. And managing a resource is a full-time job. So make an object that does nothing but manage that resource. So smart pointers are your friend. This is where I think I'm going to skip a little bit ahead because I hope you guys, anybody kind of not comfortable with smart pointers? I hope everybody's kind of got the smart pointer thing. So let's jump ahead a little bit. Smart pointer. I do want to talk a little bit about this particular thing. Here's a situation where we're calling some function foobar. We're making a new foo, and we're putting in some smart pointer. We're making a new bar, and we're putting in some smart pointer. And the question is this safe? And before you answer, I want to give you a little tip. If you're ever in a session and there's a slide that says gotcha, and the speaker says, is this safe? Guess what the answer is? The answer is this is not safe, right? So why is it not safe? It's not safe because there's many a slip between the slip and the cup. The problem is, suppose that in C and C++, parameters can be evaluated in any order. And this is a little bit of something that's a little weird because beginners expect that what's going to happen is that new is going to be called on foo. It's going to make this new pointer. So we're going to completely evaluate all the first parameter, and then we're going to completely evaluate all the second parameter, and then we're going to call foobar. The language says that all the parameters will, in fact, be completely evaluated before we call foobar, which kind of needs to be, but that any individual parameter can be evaluated in any order. And in fact, it is perfectly legal for the compiler to, or the runtime, however you want to think about it, the runtime can allocate a new bar first, then allocate a new foo, then create the smart pointer that holds the bar, and then create the smart pointer that holds the foo. That would be perfectly legal. And the problem then is that if we did, in fact, do something like that, where we create a new bar, and we haven't created the smart pointer that goes in yet, and then we create a new foo, and suppose the new foo throws. It might throw. How do we know it might throw? Because we haven't been told that it won't, so we have to assume it might. And if the foo were to throw, then what's going to happen to our pointer to bar? It's going to leak, right? Now, Howard Hinnett asked me an interesting question. He says, do you know any implementation that actually does anything that ridiculous? I don't know. That's not the point. The point is that we need to think about this case and think about how to deal with it. The problem here is that we're doing something and sticking it in the smart pointer, which is good, and we're doing something else and sticking it in the smart pointer, and it's all part of the same expression, and we don't know what order that's going to be evaluated in, and that's kind of our problem. So let's say we're going to make a rule that's going to deal with this. So we could say no more than one new in any statement. But the problem is it may not just be a new. For example, we might have, this only has one new, but I'm calling bar. Bar might throw. So we might call new foo, make the new pointer, then call bar, then put it in the smart pointer. But if bar throws, then we still leak. So having one new didn't really solve the problem. So we could say never incur responsibility of a part of an expression that can throw. Kind of the problem with that is that that's done all the time. If you just say new foo, you have a responsibility. You're going to have to clean up foo, and it could throw. So that's not a good expression. So in this case, yeah, it's actually safe because it will throw and it will create a responsibility. It never does both. So it's weird. And what about this situation? Suppose we call f, and remember f could throw, and then we're creating a new foo, and we're going to put that in the smart pointer. Is that safe? Well, there is a gotcha on the slide, but it turns out I think that one is safe. The runtime is going to see to it that a foo called. That's done at the parameter evaluation, so it's happened before the call to new foo. So that one is safe. I think I skipped a slide, but I think it may be a slide worth skipping. So one rule we could say is Demov's rule. Who knows who Peter Demov is? Oh, this is sad. This is sad. Peter Demov created the shared pointer. Shared pointer is an amazing piece of software engineering. It's brilliant. It's wonderful design. It has subtleties that you wouldn't imagine. He did this for Boost as part of the Boost. So Peter's rule was assign ownership of every resource immediately upon allocation to a named manager object that manages no other resources. And of course, Howard, who likes to make my life complicated, say, oh, wait a minute. What about a linked list? It manages a whole bunch of resources, right? Yeah, but that's his job, is to manage a bunch of resources. Basically, what he's saying is we want to make certain, and this is the problem that we had in our example earlier, that these things did not have names. These two smart pointers, they don't have names. They are temporary objects, right? And those temporary objects, they don't have a lifetime that we can guarantee. In this case, they will clean up, but we don't know that they were completely constructed before something else. And if they're not temporary objects as part of an expression, then we're okay. All right. So here's a better way. And I said this has not been updated for 14 because make unique is now in 14. Herb Sutter promised that it would be, so I called it Sutter make unique. But the truth is, this is a situation where make shared may in fact throw because the foo can throw, but the object is guaranteed to clean up if it does the right thing. Okay. So make shared, for those of you who don't know, make shared is both safer and more efficient. So it's so much better to call make shared than actually allocate an object and then stick a pointer to it in a shared pointer. Do it all once. Make shared and make unique. Make unique may be less of a win, but it's why not do it? What about this one? Is this safe? Yes, because we're not actually calling new. So yeah, that one's safe. Okay. So there may in fact be a better rule, which is don't call new, right? Of course, then how do you write your own make shared if you had to write a make shared? So maybe avoid calling new. I don't know. Or maybe keep your resources on a short leash and not let them go leaking wherever they want. Okay. So one of the things I want to start talking about now is managing state. And the idea I have is to think about state as if it was a resource. So let's think about it for a second. Let's suppose that I'm using some kind of GUI thing, and there's some kind of, we're writing to a graphic port, and there's some kind of background color. Any drawing that happens right now is going to use the background color assigned to the graphic port, right? So you have a little function, and you're going to write some widget, and one of the things that you might want to do in your widget is you need to change the background color for the widget, right? And you need to restore the background color. Now, this is not a resource in our traditional sense of a resource, but it is something we need to manage, right? And we can actually manage state in that sense, just like it's a resource. So just like we say, if you allocate a buffer, an object, whatever, then you need to release that. If you set the background color, then you need to restore it, because whoever's calling you is not expecting you to arbitrarily change the background color, right? So this is where we have resource acquisition as initialization. I don't like that, and it's not just because it sounds awful, which is Bjarne's objection to it. I just don't think it's the right thing to say. I don't think it should say resource acquisition as initialization. I think that resource includes too much. And by that, what I mean is that there's an awful lot of things that are a resource. A resource is just anything that can help you get something done. So one of the things that might help you get something done is you might be able to call the clock and say, what's the current time? Right? I mean, that's something that you might very well, you can imagine using that information to get something done. You might do it, you might be writing your own make, and you have to know, is this file before this file? And we need to know the current, whatever. You get the current time. Do you need to restore that time? What happens if you call get current time and you never put it back? Are we leaking time? Are you a time lord now? No. But, so it's a resource, but that's not what we mean. So I think resource includes too much. And the other thing is I think that resource includes too little, and this is the example I just gave. Sometimes we need to manage state. So is the background color a resource? No, it's not really a resource. But it needs to be managed as if it was a resource. So I don't like the terminology we have here. I want to say responsibility acquisition is an initialization. I want to talk about responsibility leaks and responsibility management, because that's what it's really about. I don't care if it's a resource or not. The point is, you allocated it, you need to free it. You took on that responsibility. You changed the standard font, you need to change it back. You took on the responsibility. So it's responsibility management, responsibility leaks, and responsibility acquisition is initialization. Because it's not really important that we have an object that knows how to free and get resources. It's important that we have an object that knows how to acquire and release, discharge responsibilities. So you can go around talking about RAII, and everybody thinks you're stupider than you are because you know better. You know what it really means. What it really means is responsibility. And so the guideline is use RAII. Responsibility acquisition is initialization. Every responsibility is an object. If you need to restore the background color, you need to create an object that will restore the background color in its destructor. If you need to free a buffer, then you create an object that will free the buffer in its destructor. As soon as you've done something that you are responsible for undoing, for cleaning up, whatever it is, you need an object, and we'll have one responsibility per object. It's not actually critical, but it's a better design. So, cleanup code. Don't write cleanup code that isn't be called by a destructor. Why? Because any cleanup code is something that had to be cleaned up. It's a responsibility. And as soon as the responsibility was acquired, we created an object on the stack that cleans it up. And then when its destructor is called, it releases, it discharges that. Right? So you should be very suspicious of any cleanup code that's called by a destructor. Have any of you recently seen cleanup code that wasn't called by a destructor? Hello, Joel. Joel. Remember Joel from way back in the first session? How many of you were still here from the first session? Okay, a few of you were. All right. So Joel said, do something followed by cleanup. He said, this exceptions are extremely dangerous. But what did I say when I saw that? I said the code is wrong. Why did I say the code is wrong? Because I saw a cleanup that was not in a destructor. And I said that immediately. If that cleanup was in a destructor, would Joel's problem be a problem? No. So Joel says that exceptions are extremely dangerous. Jon says that exception-safe code is extremely safe. Oh, I don't know who that guy was, but he has gray hair. So here's the guideline. All cleanup code is called from a destructor. An object with a destructor must be put on the stack as soon as calling the cleanup code becomes a responsibility. Now, sometimes we have more interesting situations, like I have an object that needs something, so I'll put it as a data member, not on the stack. But the object that has something is going to be on the stack, or it's going to be a data member of something that's on the stack. But anyway, at some point we're rooted in the stack. And the reason that's true is because what happens when we throw an exception? We always clean up the stack. The system does that for us. We don't have to worry about it. So we throw an exception, it cleans up the stack. That means every single responsibility is discharged. That is the heart. We've gotten to the third session. We finally get to the heart. All right. Here's cargo widgets example. I'm going to go through this kind of fast, but the idea is, could we get the strong guarantee? We have a widget thing. It has some type. It has two members, a type and a type. And we want to do an assignment operator. Could we have the strong guarantee? What's the strong guarantee again? The idea is that, in this case, do or do not. That's right. That's what Yoda would say. So we are going to assign the first option and then the second. And if an exception is thrown, and here's the tricky part, of course, if I overwrite this, right, and then in trying to copy over this, if that it throws, then I can't restore this. I can't undo that, right? So I can't have the strong guarantee, right? There's a real simple solution for that. You do T2 first and then do T1. All right. So here's an example of trying to do this, right? What we do is we assign the first one, and then we try the second one, and if it doesn't work, then we assign the, there's a couple of problems here. But the most important one is that this could actually throw as well, because you're doing an assignment, right? So this is not going to work. So what we need to do is we need to wrap the whole thing by another. No, it's not going to work either. So Cargill is basically saying, look, exception safety is harder than it looks. It can't be bolted on. It has to be designed in. I'm going to say, yes, we can solve this problem, but I'm going to jump ahead and talk about something else before we get to it. I'm going to talk about what I call the fundamental object functions. These are the functions that are so important that the compiler will write them for us. And I'm going to talk about the rule of three. How many of you know what the rule of three is? OK, you guys need to read more of Scott Meyer's books. Although the rule of three is obsolete now, it's a 2003. But the rule of three essentially says that if you write a copy constructor, then you also need to write a destructor and copy assignment. And if you write copy assignment, then you need to write destructor and all three of those. You either write none or all. Right? I think it actually should be the rule of four. So I think there's one more fundamental operator. Why is it? What's the reason for the rule of three? Why is that true? Well, the reason it's true is because if you're writing one of those, you're probably managing a resource. Right? If you're writing a destructor, you have some resource or responsibility. Let me say resource, like I don't know better. You have some resource that you need to, or responsibility you need to discharge. If you have to manage that in the destructor, then you probably have to worry about that same situation when you're doing a copy or you're doing an assignment, right? And vice versa. So essentially, writing any of those three implies there's some management going on that needs to be dealt with. So I want to talk about the Swapperator. This is a term that I coined because I think that swap is so fundamental we should think about it like an operator. A few years after I coined this term and started doing this, I got an email from Walter Brown, who I think is giving a talk right now. Okay, I think his talks are over. Anyway, he said it turns out he's actually proposed to the standards committee something called Swapperator, which I didn't actually think we actually needed a real operator, but I think it's two greater thans with two equal signs, or maybe it's one equal sign, and so it looks like you're swapping two things. So he actually wants a Swapperator, which I'm not. I think it's clever. I think it should be called Kalb Swapperator, but that's a different matter. Anyway, what is swap? So swap is a no-throwing. Swapping is the key to exception safety. Swap is defined in standard, but it's not no-throw in classic C++. Swap will swap two types, and we can define that. Generally speaking, we can define swap for our type as always no throw. And the reason for that is, if you think about it, ultimately every type we create is made up of some combination of fundamental types. Ints, pointers, floats, things like this. And all of these things individually can always be swapped without throwing. Now that doesn't mean that an object at a high level can be swapped without throwing, because you might have an object that you don't have access to its individual components, and you might say, well, I want to copy this over here and move it around, and it could throw. But if you're the author and you have access to all the fundamental types, then it's always safe for you to write. So we can write our own non-throwing swap for our own types, generally speaking easily, unless our type uses somebody else's type, or if our type has a const object or const data member, or if our type has a reference, something like that. So in general, though, we can write our own swaps. So when we do this, it'll be spelled swap, because we want it to be the same as in the standard. We write this is in 2003. The rules are a little bit different in 11. We'll get to that. We'll write a 1-parameter member function and 2-parameter free function in the STD namespace. So the 1-parameter function, what?
In 2003, you had to make a template specialization.
I'm getting there. I'm getting there. If your type is a template, you can't put it in STD. Because, well, we'll talk about it. You take both parameters by non-const reference. Well, duh. If you took them by value, you wouldn't be swapping them. And if they were const, you couldn't be changing the value. So it's a non-const reference, right? It does not throw. That's really important. Remember way back when I said very, very few functions need to not throw. Destructors and swap. And it is not written like this. We do not write it like swap no throw. Why? Because we deprecate that. We don't use dynamic specifications, right? Okay, so here's an example. I have this function called bigInt, and I just create a swap. Notice it doesn't say no throw, but I do have it commented, and I say will not throw. It swaps the bases and then the members. And then in the standard namespace, I make a specialization here that is a swap of bigInts, and I just call the member in this case. You could implement it however you need, but probably calling the members is as good as you can get. However, this is a little bit different. This is a template. So bigInt wasn't a template, but this is a template. It's some kind of circular buffer, and it's typed. We do the same thing, the no-throw swap, but we cannot put it in the standard namespace. Why not? Well, first of all, why was it legal for me to put something in the standard namespace anyway, right? It's the standard committee's job to put stuff in the standard namespace. Why am I putting something in the standard namespace? Can I add something to the standard namespace? No. I cannot add something to the standard namespace. This is not an add. Swap already exists. This is a specialization. It is legal for me to do a specialization on something that already exists for a custom type. Right? Now, if I wrote swap for floats, anybody using swap does not want to call my implementation, so that isn't legal. But I can swap my own types, and I can write my own definition, and I can put it in the standard namespace. And that's legal because that is a specialization. This would not be legal if I put it in. Why not? It's the same thing, right? It's a template called swap for my own type. Why is that not legal? Well, it's not legal because the standard says it's not legal. The reason it's different is just because this is not a specialization. This is an overload. I've overloaded the swap function. And the problem is there's no such thing in C++ as partial specialization for functions. We can have partial specialization for types, but not for functions. And you don't really need it because instead you just do an overload. The one thing that's different is because legally the standard says you can't do an overload in the standard namespace. You can only do a specialization. So this is how to do it. Why no throw? Well, that's really the whole point, and I'm going to show you how powerful it is that you can do swapping without throwing. So our guideline is create Swapperator for value classes, and they must deliver the no-throw guarantee. And I word it that way because we don't actually declare them no-throw. We just deliver the no-throw guarantee. There should be comment. You say this doesn't throw. This is for 2011. Let's look, for 2003. For 2011, it's a little bit different. And the reason it's different is because swap the standard swap is now defined that if it can move the object, instead of doing what it did before, so how would it do it in 2003? If you had to implement swap, what would you do? Well, you have to copy one thing to create a possibility to copy this thing over, and you go from the temporary back, right? Boom, boom, boom. That's swap. Copy, copy, copy. 3 copies and you're done. But in the standard now, what do we do instead? Well, we do a move construct, and then we do a move and another move, right? So 1 move construct and then 2 moves. Way more efficient for most situations. Obviously, if your class is nothing but an integer, then it's not going to make any difference. But generally good. But the swap is written in such a way that it checks to see if the moves are no throw. Because if they can throw, then it has to do a copy instead, right? Because it doesn't want to move out of an object and leave it in a bad state. So we move if we can, and that's why when we're writing our own move operations, it's very, very important that we make them no throw so that these kinds of optimizations all kick in. I want to jump ahead a little bit, and I think this is the place to do it. So it's kind of like the rule of 3, except now we've made it the rule of 4. I'm going to jump ahead on this stuff. This is, I mentioned my header before. If you go to exceptionsafecode.com, you can download my header. It has some checks that you can do verifications to make sure you're doing this right. I have some words about how to implement it. The code's all there. And this I do want to talk about, though. It's how to call swap in a template. So if I know that the types of A and B, then I can know what swap is going to be called. I can look at the A and B, and I can say, is there a member function of swap? I can say, is there a specialization? But what if I don't know if there is a swap for A and B? Well, I could just say std swap A and B. But the problem there is that if I have a situation like the circular buffer situation, where I have defined swap and it's not in the standard, it's not in std, then I might not get the right swap. And so the right way to do this is to introduce swap into your scope by saying using standard swap, and then you just call swap AB. And then the compiler will figure the right overload out. And it will figure out, does it need to use the standard, or does it use the one that's defined for a local scope, right? There's an easier way, well, I think easier way to do that, and that is just called boost swap. Boost swap will do the right thing. All right, so the guideline is create Swapperator for value classes. It must deliver the no-throw guarantee. That's for 2003. It's a little different for 2011 because, as I said before, standard swap already does the right thing if you have non-throwing moves defined for your class. So instead of saying create, if I want to make this work for both 2003 and 2011, I say support. Support Swapperator for value classes. For 2003, that means you have to write your own swap. For 2011, it's easier. All you need to do is define non-throwing move operations for your objects. And then the move will do the right thing. So that makes it the same for both. I don't need the 2003, 2011. So our guidelines are: do not use dynamic exceptions. Do use no except. Use it for cleanup. Use it for destructors or no fault. And move swap where else. So there's different ways to think about this. You could say wherever we can. You could look at code and you say, hey, this function never does anything that throws, so should I say no except on this function? You could say that. The problem is, if you do that, somebody comes along later, maintains your software, adds a new feature, and now it could, in fact, throw. What happens if you throw on a function that's marked no except? You're going to terminate. And you're going to go directly to terminate. You're not going to unwind the stack. It's really bad. So we don't want to go there. Now, so that's a trade-off. If you say no except, it's possible there's optimizations that could kick in. But if you say no except and you ever violate that, it's really, really bad. So what I wonder is maybe you could say wherever it's natural and free. In other words, you can't even imagine a situation where someone would modify this function to add new features that it would throw. I'm more inclined to say nowhere else. I'm going to accept that other people are going to differ. It's certainly possible in your specific case that you will actually see implementations that do have performance differences there. I won't. This is speculation on my part. All right, let's talk about the critical line. This is for situations where we do want to enable the strong guarantee. So here's a situation where we're doing this assignment operator for some object that has a resource. Is this safe? What's the problem? Okay, so you could self-assign. The very first thing we're doing is deleting something, and if you're self-assigning, you just deleted part of yourself. That's not going to be too nice. So we can fix that. Anybody else want me to fix something on the fly? Boy, am I good at fixing things on the fly. Yeah, faster. But this is still got an issue if we delete a resource and then the new throws were not exception safe. So we can fix that by using our swap, because we know that swap's not going to throw, because we're following the guidelines, and the guidelines say that we support a non-throwing swap, right? So if we do that, then we can write code like this. And in this situation, we are, in fact, still having to make the copy. You can't make that work go away. But in this case, once the copy is made, then we do a swap, and it doesn't possibly throw, right? So here's a cleanup of this. But what I want to look at is what I call the critical line. So when we're doing the strong guarantee, one approach to do this is to think about what's called a critical line. And the idea is that you draw this imaginary line through your function. Everything above the line can possibly throw, but nothing above the line can modify any invariance. And then things below the line modify invariance, but cannot throw. Does that make sense? You see why that magically works? It means if anything above the line throws, it's okay. We haven't done anything in the sense of done anything, right? But once we get that, now we have allocated everything. We've made every change that might possibly throw. And then all we need to do is maybe do some swaps, maybe do some cleanup, something else. Everything below the line can't possibly fail. So the function that we just wrote before actually had a critical line in it. I didn't call it out, but here it is. There's a line, you know, when you're creating that temporary, that could throw. But notice, nothing above there has touched any data members. Once you get to the line below here, now we're starting to muck with the data members. We're doing a swap on the data member, but notice, nothing can throw. Okay? Safe? Understand? So I got a few more examples, but what I actually want to jump to is the guideline, which says use the critical line for strong guarantees. Now I want to go back and talk about Cargill. Remember Cargill? All right. So we now get to decide whether he gave us an impossible mission or whether it was just the Kobayashi Maru. Because I'm going to look at solving his, what was the challenge again? What was Cargill's challenge? It was, can we do strong guarantee for an object that has two resources? Well, turns out you can pretty easily if you can swap. Right? You make two temporaries and then you swap. So Cargill said it wasn't possible. But I say we follow Jon's guidelines and we make a non-throwing swap and suddenly we can do the impossible. And notice the reason we can do it is because the critical line. Swap. The force is strong with this one. Yes? Yes, you can. That was part of the stuff that I skipped over. The interesting thing about that is that you can do that. Some people do that. You just copy the whole. An assignment involves a copy and a swap. That always works, is always safe, usually simple. I guess always simple. But it may not be optimized. Now consider a situation. Let's suppose I wanted to do a string that way. It's possible that I already have an allocated buffer that's large enough. And so I don't need to allocate a buffer and then swap it. I can reuse the existing buffer, right? So it's not always performant. In some cases, that doesn't matter because you're not, depends on the situation. Turns out some things we actually do have to think about. We can't just follow Guideline. All right, so we're going to talk about where to try catch. So everything I've told you so far, if you read everything that Herb Sutter wrote and Scott Myers wrote, and you go to my bibliography, everything you've already is out there. This is the only original thing in the whole 3-hour presentation I just gave you. And that is, where do we put the try catches? And I have 3 places where switch, strategy, and I could not think of anything else that started S, so I said some success. So let's talk about switch. Anywhere we need to change or switch our method of error reporting. So we may have to put a catch there, or will have to put a catch there. There's lots of places where we can't throw exceptions or propagate exceptions. And those places are where we have our guarantees of destructors and cleanup. If we're in a CAPI, an OS callback, UI reporting, it turns out that most humans cannot actually process an exception thrown at them. So we actually have to catch it first and put it in a dialog box or some other thing. And sometimes we actually are using one API where we've promised all exceptions will derive from this base class, but then we call a library that uses a different kind of exception thing, and we have to do a translate. We just catch it and rethrow a different, simple stuff. But the point is, there he is, Mr. Swapperator. Now he's going to run away. So that's one reason why we have to catch. I'm sorry, we already did the Swapperator stuff, Walter. Or maybe in threads, although in C++11, that's somewhat taken back. So that's the switch. Any place where you might have to switch your error reporting strategy, or error reporting, is one place where you have to have a try catch. The other thing is strategy, and strategy is just something where you can possibly solve the problem. It turns out in most situations, at least in my experience, in most situations, if you get an error, you can't do whatever you're supposed to do. You were told to print. The printer's not online. You're not going to sit there and wait for the printer to come back online, right? I mean, if it's an error, you just give up, right? But there are times when you may have a fallback. So maybe you have to look something up, and you find out, oh, server's not online. Well, turns out I have a cache, and I've got a fallback. I've got a strategy for dealing with the failure. So in that situation, you're going to put a try catch at the situation where, okay, if it fails, then I'm going to do something else. If you can't do anything else, you might as well let the exception propagate on up. So again, what we're asking is, the question is, where do we need to put the try catches? We need to put the try catches wherever you might have to change your error reporting in some way. So you have to catch it and change it. Or where you have a strategy, meaning you catch it and you do something else to try to solve the problem. And the other one is some success. This isn't really as important, but I actually had this in real life, and that was I had to do a database repair. And the way we did it is we read every single record to see if it was valid. And if it was valid, it would load the record, and if it wasn't valid, it would throw an exception. Well, I didn't want to terminate the first time I got an exception. So this is a situation where some success was acceptable. In other words, I get an error. I say, okay, well, I won't read that record. But when I read the next record, I'll write it out into the recovery database. Right? So it was a situation where some success was acceptable, and so I had a try catch. Right? I will guarantee you that almost all the time that you have a try catch, it will be the first case, right, where you need to change your GURP. So our guideline is know where to catch. Switch, strategy, some success. Now I want to talk about the most important design guideline. Scott Myers, you guys all know him. He's a C++ guy, right? But he actually has one design guideline. He says this has nothing to do with C++. This is universal. It doesn't even matter if you're writing code. There's one design guideline that everybody would recognize for anything you're working on, whether you're making furniture or street signs or whatever. Does anybody know what the design guideline is? Scott says the most important design guideline. What is it? It is an interface, yes. Most important design guideline. Make interfaces easy to use correctly and hard to use incorrectly. Now, this is incontrovertible. I've never heard anybody object to it. But what I have heard people object to, they say, oh, yeah, exceptions are not a good design. Well, think about this. If what we want to say is handling errors is using correctly and ignoring errors is not using correctly, then what would it be which of these follows the guideline? The one that says, oh, if there's an error, I have to jump through some hoops to process it, or the one that says, I can't possibly ignore the error? Which one fits the design guideline that says, make it easy to use correctly and hard to use incorrectly? So the guideline is prefer exceptions to error codes. Now, Nevin will give a contrary opinion, but I already gave Nevin's opinion. I promise you I did. So anyway. A few things I want to say. This is basically from Sean Parent, by the way. Throwing exceptions should be mostly about resource availability. When it's possible, we'll define behavior and/or strong preconditions instead of failure cases. In other words, we want that logic error to be asserted and caught during testing and getting out, and then runtime error is about failure cases, and we want to minimize those. Right? And then you don't use exceptions for general flow. Imagine a situation where you have a tight loop, and inside the tight loop you might have throws. That's not winning. It's not winning at all. We don't do that. So here are our guidelines. Remember, I told you they would fit on one screen. I never said what the font size would be. I said they would fit on one screen. So this is the recap of the whole 3 sessions. Throw by value, catch by reference. How many of you were here for all 3 sessions? That's really good. Okay, great. Throw by value, catch by reference. No dynamic exception specifications. Instead, we use no except. Destructors that throw are evil. Use RAII. What does RAII stand for? Responsibility acquisition is initialization. Every responsibility is an object, 1 per. It almost fits on the line. All cleanup code is called from a destructor. We will support the Swapperator, and we have to say support because in 2003 we will actually write our own Swapperator, but in 2011 we just need to be movable. That's enough. We draw critical lines in order to support the strong guarantee. How important is the strong guarantee? That's not the most important thing. The most important thing is the basic guarantee. Sometimes no throw is very important. What about the strong guarantee? When it's natural, free, and we document it. And we use the critical line to implement it. And again, if you implement it properly, you've used the critical line whether you think about it or not. But thinking about the critical line is a way of making certain you've done it the way you want to. Know where to catch, switch strategy and some success, and prefer exceptions to error code. So now we get to the fun stuff. These are some implementation techniques. These are things that might be useful for you in talking about how you're going to live in a world in which you're writing exception-safe code, you're using it, you're preferring exceptions, you're following these other guidelines. I think I'm going to skip the first one. So on-scope exit is something I wrote. Again, you can find it on my website, exceptionsafecode.com. Look for the handouts or something. I don't remember what it's called. Look for my email address if you want to find it. What it basically is allowing us to create an object that goes on the stack that does our cleanup for us. In many cases, you write a special class for that. But in some cases, you may have a one-off. So the only time in my entire application I need to call this function, and I need to call it here. I don't want to write a class whose destructor calls this function. So what do? Well, we create an object that takes a function. Here's an example. Let's skip ahead to Joel's function. So suppose that we have do something, and then we're going to clean up, and this is the only time we need to do that. We don't want to create an object to put on the stack. So what instead we do is we create an object that takes this function. And so that's what my on-scope exit does. Some of you, Andre has something. What is Andre's called? Scope guard. Bjarne had one this morning called finally. I mean, there's a million implementations. That's why I'm skipping over it. So we'll skip over this stuff. Let's talk about Lippincott functions. I learned about this from Lisa, and so that's why I named it Lippincott functions. Lisa tells me she didn't invent them, but that's good enough for me, actually. I noticed that in the second edition of the C++ Standard Library by Nikolai Jositidis, how many of you used one or the other of his 2 standard library books? Okay, that's not nearly enough. You go out here. Never mind. But anyway, on the second edition, he actually added an example of this. So what is the example? So I used to work for a company that took a product that was entirely in C++, and then they made a different UI on top of it, and they had the entire engine of the old application, thank you, in C++ underneath with a different language on top. And so we created what we called the C API, because the language on top was Objective-C, and so it understood C, but it didn't understand exceptions. So we needed to make certain that the entire API was a C API, but it was all C++ underneath, and being C++, it meant it threw exceptions. And because it was a very old code base with lots of libraries from lots of different people thinking about different things, there were lots of different kinds of exceptions. So they all had to be caught and transferred into some kind of error number that could be returned as the return value in the C API. So we had a whole bunch of code that looks something like this. We have some API status. It's an int. And then we're going to, and we say, oh, error not found. And then we call something. And if that something might throw, the something also might return an error. It's very old code with lots of varieties of things. So it might actually return an error. But if it would throw, then we would want to catch from our framework, or maybe we have some utility library, or maybe the standard exception gets thrown, or maybe some exception that some really obscure thing we haven't even found. And then we had to have some kind of function that would convert those different exceptions into an error code that we could return. Everybody understand the problem? Okay, but you don't understand the scope of the problem. Here's the scope of the problem. When I left the company, we hadn't completely finished the entire process, and we were already at 1,800 APIs. 1,800 functions that we had this code repeated everywhere. Now, if you know anything about software engineering, that's a very bad idea. You don't really want the exact same code to appear 1,800 places. Because if somebody comes along later and says, oh, we shouldn't really use this, we need to change this, or instead of calling get error code, we need to say get int error code or some other thing, or we need to add we've got a new library that we're using that we discovered in a corner somewhere that throws a different kind of exception, and we need to, if you want to modify this code, you're modifying it in 1,800 places, and that's just not a great thing to do. So what do we do instead? Well, what we do instead is we collapse all that stuff so that we have a catch which catches everything, and then we have this function that we call error from exception. And then if we want to change anything about how an exception is converted into an error, we just change this one function which is called in 1,800 places. Solve the problem, right? Okay, how many people know how to implement this function that automatically, Lisa knows how to do it, automatically changes an exception that we don't even know what the exception is. It's catch ... We don't know what the exception is. And yet we're going to magically do this. How are we going to do this? Magic. What we do is, in our function, the first thing we do is we put inside of a try, we put a throw. It's going to rethrow. Remember when we talked about rethrow, I said it throws the exception that's being processed, but I never said the exception that's being processed in this function. So it's fine for us to call another function that does the rethrow for us. And the rethrow that's done for us is in a new try catch, and all that stuff that we had before, I mean, that stuff has to appear somewhere. It's got to be here. But it doesn't have to appear 1,800 times. It gets called in 1,800 places, but it's all here. And if I have to make a change, I have to make a change in one place. It's changed everywhere. This is a Lippincott function. So another implementation toy I want to show you is something called boost exception. Boost exception is something that is an exception to my standard switch strategy in some success. Because remember what I told you is the only times you ever need to actually do a try catch is if you're going to switch how you're doing error reporting, or you have a strategy to remedy a situation, or you have some success. And the boost exception is designed to be another case. Here's how the boost exception works. It may be useful to you. I don't think it's useful in a lot of cases, but in the cases where it is useful, it can be really useful. So the idea is, remember before I said that it's possible to modify an exception. If we catch by reference and we change it and then we do a rethrow, we are rethrowing the modified exception. And so that's what the idea behind the boost exception class is. The boost exception class has essentially invented a protocol where you can add information about something that's being done and bubble that back up. So let me give you an example. We're 10 minutes in. I'm not going to give you the example. Instead, I'm going to tell you probably the single most important thing out of all 3 days, and that is how to deal with legacy code. How many of you are looking forward to writing exception-safe code? You've seen the guidelines I gave you, and you're anxious to go and live with them. Right. How many of you already live in a world where everything is already exception-safe, and you don't have to worry about legacy code that's kind of questionable? One guy almost put his hand up. Wow. Oh, there's a few people. Lisa. Can I come work for you, Lisa? Yes, you do. So you guys are all in the same situation, well, most of you are in the same situation, which is you know where you want to be, and you're here. Now, how are we going to get from here to where we want to be? And one of the problems is that we have fear, uncertainty, and doubt about all this existing code. What if I add a new function and it throws an exception? Remember, one of the guidelines is prefer exceptions. So now I have a function that throws exceptions, and the code that it's throwing into doesn't know how to deal with it, and the whole thing falls over, your boss is not happy, and we don't want to be there. We don't want to be there. So how do we deal with this? Well, we use Sean Parent's iron law of legacy refactoring, and here it is. Existing contracts cannot be broken. In other words, if I have some old code that's calling some other old code, and none of them are really exception safe, I cannot change the code down here to throw exceptions because the existing contract was that you wouldn't throw exceptions, because the calling code didn't know how to do it. So it's not good code from our standard, because there isn't a comment there that says, by the way, this is no throw, and we wouldn't want it because it's not designed to be no throw. It just happens to be no throw, so the current code works, and we got a mess, right? But in order to have reliable code and be able to go forward, we have to look at existing code and say it's not expecting exceptions. We can never have it call a function that threw exceptions. We have to maintain the existing contract. So all new code is written to be exception safe. All new code. You want to write exception safe, that's what we want to do. Let's not compromise that. All new code follows all the guidelines. It's all exception safe. Any new interfaces are free to throw an exception. However, when working on existing code, the interface to that code must be followed, because that's the contract, and we're not going to break the contract. So if it wasn't throwing exceptions before, it can't start now. That's the contract. So even though we prefer code, we also prefer that existing code wasn't bad, and we don't live in that world. So 3A is consider implementing a parallel call and re-implementing the old in terms of the new. In other words, and of course, it depends on the situation, how extensively are you making your modification, what's your difference. But one of the things you can do is you can say, okay, how would I like this function to work? If I could rely on exception throwing and such as this, you write that function, and then you write a try catch here, and you call the function, right? And then eventually, nobody's calling the old function, and you can throw it away. So here's our refactoring steps. I guess I already told you what you're going to do. You're going to have the try-catch surrounding the new call. You create a new call that does the right thing, and then eventually you retire the wrapper. The question is this actually going to work? I mean, it sounds good, but what if the wrapper never gets thrown away? Does it actually work? Well, Sean Parent, how many of you have heard of Sean Parent? You know who Sean Parent is? Yeah, he was the tech lead for Photoshop for a while. He's been at Adobe for a very long time. He actually was Alex Stepanoff's boss for a long time. He said that Adobe, they have moved multiple million line of code applications from not exception safe into exception safe using this technique. It is a tried and proven technique. Here's some of the examples. It didn't make the problem go away, but it gives you a path. You can get there, and you can do it in small bites. You never have to bite the entire elephant. You work on little bits at a time. And what's nice is there's never a situation where your code base is at risk. You never have to go to your boss and say, okay, you know what I'm supposed to be working on this week and next? Well, I can't really work on them because we're going to change the entire code base for 2 weeks and nobody's going to get any other work done. How many of you have a boss that would say, well, that sounds like a good idea? Okay, I'm not seeing any hands on that one. Okay, so the next thing I want to do, and this is kind of, I don't mean to be picking on Apple, particularly not when they've released exciting new products today, so I don't want to go there. But I wanted to show you an example of, suppose I took some code and I applied the exception-safe guidelines to it. Thank you. And what would this look like? And you're going to probably not believe this, but I'm an old Apple guy, so I went to Apple to see, do you have some sample code that I could work on? And this is literally the first thing I found. I guarantee you. I don't know how I found it, but I called it up. And I said, oh, this is good. It's got some error checking, error reporting stuff that I can work on. So what this is, and I don't even know where this is now. I don't know, maybe Apple's deprecated, but I found this many years ago. There was a call called FS, create file in open fork Unicode. But anyway, it does a bunch of things with this API that's an MBR underscore and an ACL underscore API. And they will return non-zero error codes on error, right? So what I said was, what would happen if, now I understand, I did not re-implement their code. I just said, what would happen if their code threw instead of returning an error, right? So here is what their code looked like. Can you all read that? Does that help? This is what the code looks like. You can actually read all you need to read, which is they're going to do something, and they check for a result, and if it's there, then we indent and indent and indent. There's a bunch of ifs. They keep checking. See, if result 0. That's all you need to know. It's checking to see if there's a result, and then if in turn there is a result, they free the ACL, and this is the cleanup, and otherwise they return the ACL. Okay. So I said, let's rewrite it, and here's the assumptions. First of all, we'll assume that their API throws instead of returning an error. Understand, I did not rewrite their API so that it does this. I don't have access to their code. I'm just saying, what would it look like if that's how you could call it? And then I created an ACL RAII wrapper class. What does RAII stand for? Responsibility Acquisition is Initialization. Excellent, you guys are good. All right. So I actually did 2 versions of the rewrites. The first one doesn't throw itself. It uses exception-safe code inside, but it has a try-catch, and then it reports the existing error doesn't throw. This is a model of if you lived in a world where I have a legacy code base and I can't throw. But at some point, I would like to be able to do the I can even throw, and then I can get rid of the try-catch. Okay? So here is the first rewrite. Can you read that? If you can read that, it means there's a lot fewer lines of code on the screen. And then let's take a look at the one where, and this has a try-catch in it. Let's look at the one that doesn't have a try-catch in it. Okay. Notice now that the error handling kind of went away. I don't ever say, does this fail, does this fail, does this fail, right? And the reason is because if it does fail, it's throwing an exception. And the reason, remember there was, down here, there was this little if where it cleaned up the ACL. That's done inside my capital ACL object, right? That is an object whose destructor will clean up the ACL. So if I'm in this code and any of these throw, it cleans up the ACL for me. And propagates the exception, because remember, in this version of the function, it's actually OK to throw. Right? And then when we get down to the bottom, we return the ACL dot release, because we don't want it to clean up, because we actually wanted to return the ACL. If we actually were rewriting the whole framework, we probably would return the ACL wrapper object, but that's neither here nor there. So I want to make some observations about this. First of all, I don't know if you noticed, but I added some white space here. The original actually had no blank lines in the entire original. But I've added some to make it a little easier. So there's actually more white spaces. There's 50% fewer lines. There's 100% fewer braces. Of course, I'm not actually counting the function braces. But other than that, there's 100% fewer braces. There's 100% fewer control structures. I would argue it's easier to write and read faster, and it is 100% robust in the face of these exceptions. Understand, I'm not saying every example of code you come across, I'm not saying I'm going to get rid of all your control structures, but that did happen in this example. So what does exception-safe code looks like? Well, according to Yoda, there is no try. Of course, Yoda's exaggerating a little bit. There's a few tries. But you'll notice it's what I call the coder's fantasy. What is the coder's fantasy? The coder's fantasy is, suppose you could write code and it never failed. And you don't have to worry about failure at all. You never have to check a failure. If you write a file, the disk is always there. You always have permission. You always write the file. Now that would be the coder's fantasy, and you know, as fantasies go, it's pretty harmless, but it's also never going to happen. But the power of the exception-safe coding is that you focus on the success path. Okay, I'm going to go over, but only a few minutes, and this is really exciting, so I'm going to ask you to bear with me, but only a few minutes. I got about 6 slides left. The power of the exception-safe code is that we focus on the success path. Remember the final version? No error handling visible. Does that mean there was no error handling? No. In each one of those functions, if you got down to the very bottom, if there was an error, they had to throw. My ACL had cleanup in it, inside it. But as I'm writing my code, I'm not worrying about the failure path. I'm saying it does this, and then it does this, and then it does this. If it were to fail, it's out of here. I don't have to worry about it. I'm worried about the success path. That's true of me as a reader, or as a writer, but also later when other people read it. Is it hard to follow the code? No. There's no distraction about failure. It does this, and then it does this, and then it does this. Yes, this if you were to say, I want to write it not using exception safety, but just using the fantasy, it looks exactly the same. Now again, in the fantasy, I wouldn't have had to make my ACL class handle, you know, but I do have that. But that's what it is. So here's my promise. Remember, I said at the beginning of the first session that it would be easier to read, easier to write. Easier to read meaning easier to understand and maintain. Easier to write. No time penalty. I qualified that a little. And 100% robust in the face of exceptions underneath. So, you guys' call, of course, would you rather write code like this, or would you rather write code that's handling returns, do all those kinds of things? So, why is it easier to read and write? Well, for one thing, there's fewer lines of code. There's no worrying about propagation. The propagation will handle it automatically for you when the stack is unwound. And we focus on the success path. Both as a writer and a reader, that is a huge win. I don't have to think about, okay, well, what if this, okay, and this if here, and then there's an else here, and we have to deal with this. No, it only succeeds. If it fails, it's not my problem. I've already, by making these RAII objects and putting those on the stack, responsibilities are discharged when things go wrong. All I'm worried about is, what do I do when it's right? What do I do when it's right? What about the no time penalty? Well, again, I qualified a little bit because it is possible that a compiler could optimize based on knowledge that throwing can't happen. But notice also that there's no return code checking. Now, if you're doing this a lot in a loop, return code checking, even if it's mostly successful, you're still checking. You're saying, you know, if this is 0, do this. The compiler also knows where the error handling code is and can optimize for the case where it's not doing that. And 100% robust, that's because errors are never ignored. Errors do not leave us in a bad state. When an error happens, all our responsibilities are cleaned up. Now, of course, this is assuming you write your code right. I mean, assuming you do follow the guideline. You have to decide how hard is it to follow the guideline. How hard is it to make an RAII object that's going to clean up properly? If that's a challenge, then this is going to be not the best thing. So anyway, go to my exception-safe website. Send me your resume. Okay, we've gone over by 4 minutes. I'm happy to stay and entertain questions as long as you guys are. Why don't we open some of the doors to kind of symbolically let people out if you want. But anybody wants to stay, I'm happy to entertain questions. I apologize for going long on you guys. Thank you very much.